Very good. So I want to talk to you about, well, effective BV actions for Chern-Simons on cylinders and Chern-Simons-like theories. This is a joint work with Alberto Catania and Konstantin Wernli, and here's the archive link. And this sort of this link follows the quantum side of the story. There's also a classical counterpart, which is sort of interesting from a symplectic geometry point of view, and it is in the accompanying paper. So I know that there was a mini course by Alberto Catania on Bv Bfv formalism, and a talk by Michele Schiavina, which was using Bv Bfv formalism, so there will be some overlap. So the setting roughly is like that. So we want to consider some, well, topological theory, well, Chern-Simons or Chern-Simons-like, on an interval cross some manifold, well, let's say a surface. So we have some kind of a Chern-Simons-like theory in the bulk. And so on the boundaries, so this is a cylinder from, I don't know, some initial time to some final time times, well, let's say a surface. And so at the initial and final time, we want to impose boundary conditions, or more precisely, kind of a family of boundary conditions. So we want to actually impose some boundary conditions given by Lagrangian fibers of some polarization of the phase space. So we fix some polarization, let's say vibrating polarization of the phase space at initial time and the polarization at the final time. So polarization P initial and P, well, out. So then, given given boundary conditions belonging to those polarizations, we can calculate the effective action, so the path integral with boundary conditions, or kind of partial path integral, sort of integrating out everything except for some small space of residual fields, and then we construct the effective theory on residual fields. And this theory, okay, so it is some interesting theory, so it's interesting to calculate what you are getting. And in the examples that I will be talking about, you will be getting some kind of conformal field theory on that kind of transversal surface, which is interacting with this boundary fields. So the base of the polarization on the inside and the base of the polarization on the outside. So for instance, for abelian Chern-Simons, depending on which polarization you choose, you could get two-dimensional massless scalar theory interacting with boundaries, or you could get the beta gamma system interacting with boundary fields, depending on which polarization you have chosen. For non-abelian Chern-Simons, you will get essentially coset WZW model for one choice of polarizations, for the other some sort of more complicated relative of WZW model. And there is also an interesting sort of higher dimensional example, which I will mention briefly, where you put 7-dimensional abelian Chern-Simons in the bulk. So sigma in that case would be a Calabi-Yau threefold. And you put some, so there's some kind of interesting choice of polarizations to put on the sides, where one of them is a kind of a linear chiral polarization, the other is some non-linear polarization. And then what you get as an effective theory is something quite interesting, and it's related to this BCOV theory, Birshatsky-Chikoti-Oguri-Waffa, where the field is essentially a deformation of the complex structure on the Calabi-Yau threefold. Okay. So now I want to very briefly recall the setup, and I know that it was already spoken about this program, so I will be brief. So how Bv Bfv setup works, so I need to say something because I'm using it. So on the classical side, it's the setup, so it's an extension or refinement of Batalin-Vilkovisky formalism to manifolds with boundary, where you're allowed to glue and cut. So that's what it is. So it does the following. So to a manifold with boundary, it assigns certain supergeometric packages on the classical side. So to the bulk manifold, you assign the graded supermanifold of fields endowed with a cohomological vector field. So usually you call the structure a DG manifold. And with a degree -1 symplectic structure and a degree 0 action. And then to the boundary, you associate its phase space, or the space of boundary fields, with its own cohomological vector field. So it's also a DG manifold, with its own symplectic structure, which is even, and moreover, you ask for it to be exact, or in a slightly more general context, you would ask it to be the curvature of some pre-quantum line bundle on the phase space, but I don't really need that generalization here. And also you want some degree +1 function of the BFV function of the BFV action, which is the Hamiltonian for Q boundary. So also part of the data is well, surjective submersion from the bulk fields to the boundary phase space. And so the relations here are that Q on the boundary is the projection of the Q in the bulk. And also, well, the relation that, well, Q's square to 0. The relation that Q on the boundary is the Hamiltonian vector field generated by S boundary. And sort of the maybe more kind of non-trivial relation, so relating the bulk to the boundary, that if you contract Q with omega in the bulk, you obtain delta of S bulk. So delta denotes the RAM on the spaces of fields and phase spaces, as opposed to D, which is kind of the geometric DRAM on M. Plus a defect. And defect is controlled by this boundary one form. So this is the sort of classical Bv Bfv package, and essentially, yeah, so you can sort of do these exercises and cast various gauge theories into this formalism, and well, it works very well. So on the quantum side, you have something else. So to the bulk manifold, okay, let me first say about the boundary. So to the boundary manifold, you would assign a chain complex with differential omega. So this complex is the space of states. The omega is the quantum BRST operator. So in particular, you want it to square to 0. And to the bulk, you assign two objects. So one is certain odd symplectic space, the space of residual fields. And also you're assigned to the bulk the partition function, which is an element of the space of states for the boundary tensored with functions on the space of residual fields. More precisely, it should be half densities rather than functions, but let me omit this subtlety. So essentially, this kind of tensor product structure is the kind of the signal that the construction here is a mixture of two constructions. One construction is path integral with boundary conditions, which corresponds to the first part. The second part is the construction of effective action, which contracts you from kind of the whole space of fields to some, by integrating out some subspace of fast fields, gives you a function on slow fields. So that corresponds to the second part. Okay, and the structure relation here is the master equation, or modified quantum master equation. So modified stands for the contribution of boundary. And it says that Z is killed by certain operator, and that's just the sum of omega boundary. And then with some coefficient, the Bv Laplacian on the on the residual fields. So Bv Laplacian corresponding to the odd symplectic structure. Okay, so this is sort of the data. So the quantum Bv data, and well, you produce it at least in the sort of zeroth approximation by the following idea of quantization. So how to pass from the classical package to the quantum package. So it goes like that. So, well, you first need to fix a polarization of the boundary phase space. Let's say vibrating Lagrangian polarization. So, and moreover, you wanted to have the property that this boundary one form vanishes along the fibers. So then, okay, you say that, well, it's a very, very easy case of geometric quantization, and you are constructing the boundary space of states as just functions on the base. Or you could say functions on the phase space, which are constant along the fibers. Okay, and so also in the first approximation, you would be constructing the BRST differential as well a geometric quantization of this BFV function. And well, of course, there could be a problem of ordering and problem of whether it squares to 0 or not. So well, hopefully there is some ordering where it squares to 0, or there are actually so okay, this is the zeroth approximation. Then there's sort of a class of cases where you are actually constructing omega by, let's say, configuration space integrals rather than canonical quantization. So okay, now there is also the space of bulk fields, which projects to the boundary phase space, and we are interested in the fibers of the composite projection from the bulk fields to this base of the polarization. So fibers of this map are essentially fields with fixed boundary condition. So with boundary values given by some Lagrangian in the phase space belonging to the family given by the polarization. So, and let's say that, let me denote why the fiber of this composite projection. And then let's say that I split my fiber into some small part, the slow part, and the fast part. So let me denote V, the slow part, and Y prime, the fast part. So slow part I call residual fields, and the fast part, well, I don't know what to call it, fast fields, or the complement of the residual fields. So I want this to be a symplectic splitting, so compatible with the odd symplectic structure. Then okay, so then this V exactly goes as a part of the quantum package here with its odd symplectic structure. And the partition function is, so the idea is the following, that it depends on a boundary condition, so on an element of B boundary, and on a residual field. And what it is the following. So you take the exponential of the action evaluated on, well, you have fixed a point here in the base. So now you're in the fiber over that point. In that fiber, okay, this fiber is split in this way. So you're fixing a residual field, and you're integrating over an element in Y prime. Let me call it phi fluctuation. In fact, I want to integrate over a Lagrangian inside of Y prime. Well, this is a BV context. I need to cut out a Lagrangian for integration. And this is the gauge fixing Lagrangian. So yeah, that's the idea of the construction. And well, you can of course interpret it as this function that you're producing as an element of, well, the space of states constructed this way times functions of residual fields. All right, so this is sort of the idea to be made sense of in examples. Now, let me sort of transition to the very, very trivial example, well, which will kind of lead us to Chern-Simons on cylinders. Okay, so one-dimensional abelian Chern-Simons. So it goes like that. So the space of fields. So this is an AKZ model, and I'm sure that AKZ models are kind of discussed in this program, and they don't need to explain what it is. It's like an AKZ model on the mapping space from the odd tangent bundle of the interval to, let's say, the purely odd vector space, so the parity shifted vector space, where H is, well, okay, some vector space with a fixed inner product. With an inner product. Okay, so I is the interval 0 to 1, and an element here is, okay, it's a non-homogeneous differential form with coefficients in H with appropriate in parity. So it has a 0 form part and a 1 form part along the interval. So the 0 form part is okay, 0 form with coefficients in H, which is intrinsically odd. A is a 1 form, which is intrinsically even with coefficients in H. So then the kind of the bulk Bv data is given by the action, which is the integral over an interval of, well, A superfield comma dA superfield, or, well, of course I can actually only the 0 form component survives here. Then there is the odd symplectic form, which is, well, I can write it either in superfield or in components. So let's say in component, it is this one. There is the BRST operator, which is essentially the integral of d psi d over dA. So I want to say that what I'm explaining here is a very simple example, this abelian Chern-Simons. It has actually the non-abelian version of it is quite interesting and leads to rather non-trivial formulas. And this one we studied with Anton Alexeyev in 2010. But I don't need those formulas now. So actually I want to look at the abelian one here. So the boundary, so this was the bulk data. The boundary data, okay, so I have my interval. It has 2 boundary points. You could say with a point with positive orientation, a point with negative orientation. Let me explain the boundary data for a single boundary point. So the phase space for a boundary point is just my odd vector space, and the one form sitting there is 1/2 psi delta psi. And, well, this BFV function is just vanishing, and the BRST homological vector field is also vanishing. Okay, this is the classical Bv Bfv package. So it's a very straightforward exercise to check the axioms here. For instance, the structure relation, which was this one. This corresponds to this computation where you calculate the variation of S or derivative of S on the space of fields, and you do the integration by parts, and you will obtain the bulk term corresponding to contraction of Q with omega, and sort of the boundary term, which is the pullback of alpha boundary from the 2 endpoints. So yeah, that's computation, which is sort of maybe a BV incarnation of the standard computation what everyone does in classical mechanics for variation of action. So, all right. Now for quantization. So I need to impose some additional data. So I want to split. Actually, let me erase those markings because they could be confusing, plus and minus. So for quantization, I need to choose polarizations. Let me fix a Lagrangian splitting of my H, my coefficient space. So Lagrangian with respect to the inner product. So if my inner product was positive definite, then to do this, I would need to do a splitting over complex numbers. If it was, let's say, of signature n, then I can do it over reals. Okay, So then what I want to do is I want to fix the following polarizations. So at t equals 0, I want to fix the plus component, so component in H plus of the field psi. So I should have mentioned that the projection from the bulk to boundary fields is just the pullback of a differential form to a boundary point, and so it forgets A entirely and restricts psi, the 0 form, to either t equals 0 or t equal 1. So my kind of boundary phase spaces are parameterized by psi, and well, I'm saying that my polarization at the in boundary would be to, well, remember psi plus, so fix the value of psi plus. So there's a Lagrangian hanging over it, given by different possible values of psi minus. So I'm fixing psi plus at the inside and also psi plus at the outside. I could have chosen it differently. It's analogous to, I don't know, in classical mechanics, you could consider a problem where you fix initial coordinate and initial and final coordinates, or initial momentum and final momentum. Okay, so then my space of bulk fields, well, it's first of all, it's fibered, it projects into the kind of phase space for initial time and phase space for the final time. And then by polarization, this projects to pH plus, which is the base for the initial polarization, and also pH plus, which is the base for the out polarization. Just due to our choices, we could have made different choices. So this is B initial and B final. So the fiber of this composite projection, that's the thing that we are interested in. So that corresponds to fields with fixed boundary condition or fluctuations around a fixed boundary condition. So that's what I denoted Y curly. So the fiber is given by differential forms relative to the boundary, so vanishing on the boundary with coefficients in pH plus. And because if I'm concentrating on the plus component, then, well, there's no restriction on the one form, but for the 0 form, its plus component should vanish, the plus component of fluctuation around the boundary conditions. And also differential forms without any boundary conditions with coefficients in H minus. Now I need to do some splitting on this. Yes, please.
Can you explain again why they should take values in pi H plus? I didn't get it.
So this is a choice of polarization, right? So let's imagine that. So this is a choice of polarization. So I'm choosing, let's say it was an even situation. There were initial Q and initial P and final Q and final P. So I could have fixed initial coordinate Q and final coordinate Q. So then for the fluctuation around, so if I'm presenting my field as some extension of Q initial in the bulk and some extension of Q final in the bulk, then to it I should be adding a fluctuation which has to have vanishing Q at the initial time, vanishing Q at the final time, but no restriction on P.
But this is about the one form, so it confuses me, right?
No, that's about 0 form. This DI, it's actually it doesn't affect the one form part.
This is omega 0?
This is omega bullet, because I want to write it this way because then it's a complex. But
one forms also.
Yes, so vanishing on the boundary means vanishing, the pullback to the boundary vanishes. It doesn't affect one forms.
So why omega bullet? Why the one forms need to take values in pi H plus and not everywhere?
So they take values everywhere. I'm just splitting it into two parts. So this is the part in H plus, and this is the part in H minus.
Okay.
I just wanted to split it explicitly into two complexes: the absolute theorem complex and the relative theorem complex.
Okay.
Okay. So then, and this is sort of instructive for what I wanted to write down for my space of slow fields, the residual fields. Actually, this is the smallest choice that I can make, which will lead to a well-defined well-defined integral. And I would just take the cohomology, the de Rham cohomology along the interval. So it will be relative cohomology with coefficients in H plus and absolute cohomology with coefficients in H minus. So, and I can actually promote this passage to cohomology to, the deformation retract, so I can construct an inclusion of cohomology by some representatives, the projection, and a chain homotopy contracting Y to the cohomology. And that's actually the data that I do need. So it gives me the following splitting. So first of all, I'm splitting my Y into cohomology or representatives of cohomology, which is, let's say, dt, so where t is the parameter coordinate along the interval, dt times pH plus, well, because, well, this cohomology is spanned by dt, plus 1 times pH minus, because, well, this is the absolute cohomology of the interval spanned by the constant function 1. And then, okay, I have a complement, and here I should just take the symplectic complement, symplectic orthogonal of V. So that's a well-defined thing. And then inside that, I need to split it into the exact part, the exact part. So let me call Y prime this symplectic complement, but I want to split it into two parts, the exact part, and I need to choose a chain contraction K. So Y prime is acyclic, so I need to, well, choose a contraction. In fact, in this one-dimensional theory, the contraction is unique. And I will write it to you in a second. But so this the exact part will be, okay, what it will be 1 forms on the interval with coefficients in H plus with vanishing integral, because, well, it's a symplectic complement, it should pair by 0 to this part. And 1 forms on the interval with coefficients in H minus and no restriction, because, well, I mean, pairing to that part doesn't impose any condition on the 1 form part. Now, the K exact part will be, well, actually everything else, the 0 forms. So the 0 forms with coefficients in a pH minus with vanishing integral against dt, and that just comes from the symplectic orthogonality condition, and 0 forms on the interval with coefficients in pH plus. All right. Yeah, so this is kind of a Hodge decomposition, or maybe somewhat generalized Hodge decomposition, because it's not corresponding to splitting into D star exact and D exact and D star exact, and instead sort of you're choosing a different chain contraction here. Let me write it down because it's important for us, this chain contraction. So chain contraction is a map from Y prime, sorry, from Y prime 1, so the 1 form components, to Y prime 0 forms. So it should be a map of degree -1. So, okay, and it is an integral operator. So it sends a 1 form into an integral of that 1 form against some kernel law, Green's function or propagator. The integral over T prime running over the interval. So, and then I can write for you what is this this integral kernel or propagator. And here it's really, there is no choice due to low degree. So it is the projection to the plus component of H times the following function. So the step function of T prime minus T plus pi minus times a similar expression T prime minus theta of T minus T prime. Did I mess it up? No, let's see, might have messed it up. So, okay, then this gives us the gauge fixing. So the Lagrangian over which we are going to integrate is exactly this Y prime K exact, and it's a Lagrangian inside Y prime, and this is the only choice of Lagrangian which gives a well-defined non-degenerate integral with non-degenerate quadratic form. Then you just do this exercise. So essentially you do exactly what was proposed in this formula. So you need to split your field, your superfield, as well, as kind of the boundary field plus the residual field plus the fluctuation. So you're splitting your field as the boundary field, psi plus plus psi minus, but I should sort of extend them into the bulk. Let me denote twiddle this extension. In fact, I want this extension to be concentrated close to the boundary. So psi plus in should be an extension by a bump function close to the boundary of psi plus in. And in fact, I need to take the limit of the support of this extension going closer and closer and closer to the boundary. So I mean this particular limit. So then there will be the residual fields. So the fields here. So it will be 1 times psi minus plus d psi minus residual plus dt times a plus residual. So that's just an element in V. So a plus residual is an element in H plus, psi minus residual is an element of parity shifted H minus. Okay, and then there will be the fluctuations, and there's the kind of the 0 form component and the 1 form component. So the 0 form component is here, the 1 form component is here. Actually, sorry, I forgot to say that this differential forms should be relative to the boundary, and well, actually, this also relative to the boundary. Forgot to write it. Apologies. Sorry, no, only one of them are relative to the boundary. Which ones? The ones which are in H plus are relative to the boundary. The ones with coefficients in H minus are not relative to the boundary. Sorry, messed it up. So there's relative to the boundary sitting here. So this means that my psi plus is a kind of odd scalar. Sorry, my psi is an odd scalar, and this plus component vanishes on the boundary. Its minus component should integrate to 0. So psi plus fluctuation on the boundary should vanish, and its integral, the integral of psi minus component should be 0. Those are the conditions. And well, there's also this A fluctuation, but actually it's killed by going to the Lagrangian, to the gauge fixing Lagrangian. And then, okay, we're just doing kind of our exercise so we know, okay, what's the quantum sort of data here? Well, the spaces of states are just functions of psi plus, so function of pH plus for the out boundary with 0 differential. Functions on also pi h plus on the in boundary. So you can think of those spaces as spinor modules, although this structure is not terribly important for what I'm about to say. But I mean, local quantum observables can be identified with Clifford algebras, then it's important that those are the spinor modules. So now I described for you what is V, the space of residual fields. And the partition function is calculated by the integral over this fluctuation field of the exponential of action. So, okay, now in this action, there's a subtlety that I need, which I denoted by this little f. Little f means that I need to include certain boundary terms. Why do I need to do that? That's because I want a compatibility between the 1 form on the boundary induced by the differential of the action with polarizations that I like. And I told you that I like some particular polarizations, so these ones. Whereas the 1 form that's induced by the action in its default form, it is this 1 form, and it doesn't vanish on those polarizations. But I can make it vanish by doing some transformation. So there's this transformation that you can always do. You can shift the action by adding to it a pullback of some function of boundary fields, and simultaneously shift the boundary 1 form by the differential of that function of boundary fields. And you can use this transformation. So you have some alpha initial, which is not which comes from the differential of S, but which is not compatible with polarization that you like. But then you can try to choose some clever F so that this combination is compatible with polarization that you like. But then you should include that F as a boundary term for your action. So that's the idea. And here we can, of course, do that. And the action will be, well, our original action, ADA, 1/2 ADA, plus, oops, making a mess here. Making a mess. So plus some boundary terms. So psi plus paired with psi minus at the out boundary, minus, psi plus paired with psi minus at the in boundary. And well, when you do that, then you have this compatibility condition. Then the variation of the action with these boundary terms will be some kind of bulk term, which is, well, contraction of Q with omega, plus psi minus delta psi plus at the out boundary, which is compatible with the polarization given by fixing psi plus, and psi minus delta psi plus at the in boundary, which is also, which one is, okay, one is at the out, the other is at the in. So they are both now compatible with polarizations that we like given by fixing psi plus. So just wanted to comment on those boundary terms. And then, okay, you're just plugging in that expansion of fields that I gave, and then it becomes a Gaussian integral. So there are, I don't know, a couple of Feynman diagrams contributing there. But the result is the following expression. So it's psi plus out minus psi plus in paired with the residual field minus residual fields. So let me call this object the effective action. So my partition function is the exponential of the effective action. So I have effective actions that depend on my residual fields and on the boundary fields. All right. So I'm sorry, I realize that I'm a bit tight on time, so maybe I should not be guiding you through the Feynman diagram computations. It is very simple here. So you do have the modified quantum mass equation. In this case, it's trivial, really. So it becomes non-trivial in kind of deformations of this example. So here the boundary differential is 0, and the delta residual is just the second order differential operator. The different derivative in psi minus residual, derivative in A plus residual. Obviously, this does not depend on A plus residual, so therefore it's satisfied trivially. So, well, one thing I should mention is that if you take the same problem but change the boundary polarizations, now you fix psi plus at the out boundary and psi minus at the in boundary, then now the corresponding fiber of fields over boundary conditions becomes sort of a sum of two terms where they will be differential forms relative with coefficients in H plus relative to the one endpoint, and differential forms with coefficients in H minus relative to the other boundary points. Since differential forms with coefficient relative to a single boundary point is actually a contractible complex, then this Y is actually acyclic. There's no cohomology. So you can choose V to be nothing. And therefore, this is a particularly simple example. There are just no residual fields, or you can choose the space of fields to be empty. Generally, you can choose any deformation reject of Y to be a space of residual fields. But for this smallest possible choice, the effective action is just psi plus out paired with psi plus in. So, but this is just to illustrate a phenomenon that the space of residual fields, or the smallest space of residual fields, depends on sort of the transversality properties of your two polarizations at the in and out boundary. And in the linear context, when they're given by kind of parallel translates of two fixed Lagrangians at the in and out boundary, the space of residual fields can be understood as a derived intersection of two Lagrangians. So depends on these transversality properties. Well, as in these two examples that I've shown, residual fields has different size. All right, so now I want to go to the kind of deformation of this example in several directions simultaneously. So I want to go to three-dimensional abelian Chern-Simons. So on an interval cross a surface. So first of all, the one important deformation is that I still will think of it as a one-dimensional field theory, but with coefficients. So the fields will be differential forms on an interval with coefficients in forms on a surface, well, with a shift by one. So this is now my coefficient space. So I'm thinking of Chern-Simons on a cylinder as a one-dimensional theory with infinite dimensional target. But this target now carries, it's not just a space with a pairing coming from Poincare duality on sigma, but in addition, it carries a differential d sigma, which is a sort of gives you a target, a KZ Hamiltonian. So then, so your action that you start with is now, well, a d on the interval a plus kind of the target part, a d sigma a, which we understand is a perturbation. So this leads to kind of a presence of more diagrams coming from this perturbation. So let me see how, yeah. So the picture is like that. So I'm considering a surface, closed surface cross an interval from 0 to 1. I want to fix the boundary conditions, boundary polarizations by fixing. So let's say that I fixed a complex structure on the surface. So I want to fix A0 at initial time, the ghost.
There is a question.
Yes, please.
And why don't you just consider that ADA? What is the advantage of taking this very simple quadratic term to be like a perturbation or something?
Somehow it's crucial to the formalism. I'm hearing an echo from myself. So it's crucial for the formalism. Let me see how to explain this. Well, it is essentially because of how we want to treat this theory. So we want to treat it as a one-dimensional theory, or currently as a three-dimensional theory with axial gauge fixing. So with a very special gauge fixing. So our propagators will be corresponding to the chain contraction 4di. It is a choice. So it's not, I don't know, the more usual way of doing Lorentz gauge fixing, let's say, which would correspond to kind of inverting up to homotopy the total differential. I want to invert up to homotopy only di, and this is the way how I can incorporate the polarizations that I wanted to use. And actually, I don't know how to do it with the Lorentz type boundary condition.
Can one say that you are doing just like Hamiltonian formalism and Hamiltonian quantization and Chern-Simons? You split the time and the rest.
It is well, it is a close idea, right? It is a close idea, but I think I explained what I'm doing. It's a one-dimensional theory with infinite dimensional target, right? Which you can do for this particular geometry, but it also it forces on us a particular gauge fixing, which is what I was trying to say. So, okay, so let me try to continue. So I want to impose the chiral gauge fixings, chiral polarization, so this particular one. So 0, 1 and 1, 0 components of the one form field at the in and out boundary, and sort of the ghost field of 0 form component should be fixed at the in and out boundary. So these notations correspond to the three-dimensional sort of notations for the Deram components of the AKZ superfield. So the 0 form, 1 form part, 2 form part, and 3 form part. Sort of it's hard to find good notations here. And then again, you play this game. So you expand your fields, your superfield into the extension into the bulk of the boundary fields, plus the residual fields, which I need to tell you what they are, plus the fluctuations. And well, the fluctuation, there's the 0 form component along the interval and the one form component, and on the gauge fixing, the one form component will be killed. So the residual fields, they are given by, let me call it field sigma, which has ghost number 0, which is a 0 form on sigma, or more precisely, it should be thought of a relative cohomology on the interval relative to the boundary with values in omega 0 of sigma. And there's a star residual field, which has ghost number -1, which is in omega 2 of sigma, or more precisely in the absolute cohomology of the interval with coefficients in omega 2 of sigma. Now, then you play again the game that I explained. So here the game is kind of made more interesting, mainly by the presence of this differential in the target. And you will obtain the effective action. So let me write it down. So let me start with the term that I think is most interesting. Del sigma, del bar sigma. And then terms where it talks to the boundary conditions. Let's see, A10, A01, so out and in, and also the ghost term. So I think that the most interesting term here is this one, the first one. So this is the scalar, massless scalar, and so it's in particular it's a conformal field theory, where the field is the bosonic part of our residual fields, and then it's extended by interactions with boundary and by certain also ghost term. So, and it appears here from a particular Feynman diagram. So there's
what is sigma again?
A sigma is a 0 mode, or residual field. Sorry, residual field. So more exactly, it lives in H1 of interval comma a boundary of the interval with coefficients in omega 0 on sigma. So it's a function on sigma ultimately, but this is how it arises. It arises from relative cohomology, but it also explains its ghost number, right? Because the coefficients should be in omega shifted by 1, but it's also a 1 form. Therefore, it should be a field of ghost number 0. Okay, so now, yeah, I wanted to say that this comes from a particular Feynman diagram where there are two points kind of traveling on the interval connected by a propagator, or traveling on the interval across the surface, but our propagator contains a delta function in the surface direction. So a double integral over a surface becomes a single integral over a surface from the delta function in the propagator. But there is some non-trivial sort of structure in the propagator in the interval direction. So there is some little integral to calculate there, which gives this 1/2. Okay, and then maybe just a remark that if you do the sort of instead go for a slightly different polarization, namely you fix A10 and A10 on the sides and ghost on two sides, then, well, you calculate the space of residual fields by this sort of relative cohomology construction that I was explaining, or if you want to be more fancy, by derived intersection construction, then you have more residual fields. So you have the ones you had before, sigma and A star residual, and in addition, which are again 0 form and 2 form on sigma of ghost numbers 0 and -1. But in addition, you also have some additional 0,1 form on sigma of ghost number 0 and its sort of counterpart or its anti-field, a 1,0 form with ghost number -1. And then the corresponding effective action will be, let me just write a part of it, the part again that I think is more interesting, where it's lambda del sigma plus various interactions with boundary fields. And this part, which depends only on the residual fields, so here if you look at it, you recognize the beta gamma system, the conformal beta gamma system. Now, for the non-abelian story, so fortunately, yeah, I'm in negative time. Let me just show you. Fortunately, I have some slides which at least outline the story. So in the non-abelian case, it's like the abelian case, but you have an additional vertex coming from the a cube term in the action. And this leads to having more diagrams. But I'm using, again, this A01, A10 polarizations, where the only residual fields are sigma and A star. There's a bunch of diagrams that appear actually manageable. So you can, not that bad, nothing beyond one loop. And well, you start computing this diagram. So there are some interesting configuration integrals over configuration space on the interval to compute. And these integrals give you, depending on which diagram you are staring at, either something like 1 over n factorial, where n is the length of a diagram, or something like Bernoulli number, depending on which diagram you look at. And all those assemble into this expression. So maybe I should comment that, yeah, there's kind of a part which is maybe the most interesting part really is this one again, which depends only on the residual fields. Then there's a part where boundary fields appear. I don't know, make it purple. And there is the one loop part, which is, okay, which requires some regularization, like replacing sigma with like a cell decomposition, for example. So because, okay, there are two kinds of diagrams, and one kind of wheels just vanishes by our choice of gauge fixing, and the other doesn't vanish. And instead it gives something like sum over points of sigma of some well-defined expression. So it's more like you obtain something like trace over differential forms on sigma cross I of something of, well, the tensor power of chain homotopy operation. Sorry, not tensor power, well, some just nth power essentially of chain homotopy operation. That's the value of this loop diagram. And here the supertrace over the interval can be calculated, it's well defined, whereas the supertrace over differential forms becomes the sum over points. It's not really well defined. So, but then you can and should understand it as a correction to quantum measure. So due to its form. And actually what you can do is change your parametrization on the space of residual fields to, well, make a change of variables there to a group-like variable, the exponential of sigma, and its Darboux counterpart. So it's given by a complicated formula, but it's just tuned in such way that integral of dg star with dga is exactly your symplectic structure. So it's the usual group valued field on the surface and its Darboux counterpart. And in terms of those variables, actually your effective action has a very neat form. It is the WZW action, Vezzo-Minuitin action of G, plus its interaction with boundary fields, with this chiral boundary fields, plus certain ghost term. So this first line is commonly called G over G WZW action, or coset WZW action. So here it appears as an effective theory on residual fields. Now, it satisfies a quite non-trivial quantum master equation with boundary terms. So these boundary differentials, they do appear as sort of the naive canonical quantization of the BFV action in our polarization, so no corrections needed here. So yeah, maybe I should stress that there are no quantum corrections to this formula. I mean, it's a formula on the quantum level, but there are no H-bar corrections anymore. So, and I should say that the connection from the previous formula to this one is not changing variables as in a function, but changing variables as in a log half density, which absorbs this Jacobian. So this turns out to be exactly the Jacobian of our change of variables. Okay, and then I should mention that, okay, so you have the modified quantum master equation. And well, it corresponds, or it's certain truncation of it corresponds to Polyakov-Figman formula for the WZW action. And there's certain symplectic geometric interpretation of the result, which connects to Alberto Catania's lectures before, but maybe since I'm in a very strongly negative time, I should not go there. Essentially, it gives you a generating function for the Lagrangian in the product of the two boundary phase spaces for the top and bottom of the cylinder, given by a restriction of flat connections to the in and out boundary. And so there's a generating function in upper. Yes, please.
Some questions. There were some questions, so you can have a few minutes more.
Okay. No, thank you very much. So nearing the end. So yeah, what I wanted to say is that this this action, it can be understood on the classical level as so-called generalized Hamilton-Jacobi action. So if you take the differential of the graph of the differential of that action and do certain symplectic reduction, which kills the G field, then you obtain a Lagrangian in the product of the two phase spaces for the in and out boundaries, which is the dynamical Lagrangian generated by the dynamics of the system. So it gives you the restriction of flat connections in the bulk. So solutions of equations of motion in the bulk to the in and out. Okay, so I sort of, here is this symplectic reduction part sitting here. Okay, now I wanted to, there are two little points that I wanted to make. One is that, okay, you have this, you can again consider the theory with 1-0 initial conditions and 1-0 boundary condition on the inside and 1-0 on the outside, and ghost fixed. So this extends this beta gamma system story that I mentioned before. And then you get some effective action, which again depends on the same package of residual fields as in the beta gamma example. I'm sorry for notations. This I denoted lambda and lambda star previously. There's really no good choice for notations here. It's always a mess. So the resulting effective action is something I denoted W twiddle. And with sort of a good change of variables on the space of residual fields, it's this aggregate. So it's related to WZW action, which again interacts to this more complicated system of residual fields and also the boundary fields. So the beta gamma term in the abelian case is this term, and also contains some interaction with ghosts. And again, it satisfies the quantum master equation. And what I wanted to mention here is that there's this diagram. You can, look at Chern-Simons on a cylinder with these two possible choices of boundary conditions. So in one case, you get this coset WZW with ghosts, which give you an interesting master equation. You can pair it with boundary states, particular boundary states, which just set those boundary fields to 0. So those are particular omega closed boundary states. If you do that, you get the pure WZW. So, which, well, I don't really understand this word, but people say that this is the holographic counterpart of Chern-Simons. So, okay, then you also have the following picture that you can glue the two sides of the cylinder into a torus. So you can obtain a circle across the surface. And then there is, you can calculate the effective action on the smallest model for residual fields, which is just cohomology of the circle tensored with differential forms on the surface. And these are just two copies of differential forms on the surface, which you can identify with the A and B field of the two-dimensional BF theory. And actually, the effective theory is the non-abelian two-dimensional BF theory with certain subtlety, which I emphasize here by the word compact. So it has some additional large gauge transformation acting on the B field coming from the circle direction. Okay, and in this picture, sort of there is, you can forget everything about the three-dimensional part, and then there's some master object, this WZW twiddle, from which you can transition on one side to 2D BF theory by sort of gluing to some state corresponding to a short cylinder, changing the polarization here, and then doing the gluing of the ends. And on the other side, you can do this transition by doing the Siegel-Bargmann transform on one side from holomorphic to anti-holomorphic field and integrating out the redundant residual fields. So this is in some sense an equivalence, and well, this in some sense is not, because you're pairing to a state. And okay, this is not an equivalence, and this is not an equivalence because, well, you are also pairing to states. So pairing to states is not supposed to be an equivalence. It's like taking a matrix element of a matrix. So there is this kind of master object, which in some sense sits between the holographic counterpart of Chern-Simons and the dimensional reduction of Chern-Simons. So I wanted to mention that point. And just, to show this slide, and maybe as an advertisement for another example that we looked at, you can consider this 7-dimensional abelian Chern-Simons on a Calabi-Yau threefold cross-n interval. And you can fix, again, kind of a linear chiral polarization on one side, coming from a complex structure on your Calabi-Yau. And so it's an abelian theory, again, ADA theory. And on the other side, you fix some, it's called Hitchin's nonlinear polarization on 3 forms on a Calabi-Yau. And for the other forms, you choose essentially fix the ghosts. That's essentially what you do. And for the 3 forms, which are kind of the ghost number 0 component, you do something tricky. So you split a 3 form into 2 fully decomposable 3 forms. So the wedge product of 3 1 forms and wedge product of 3 other 1 forms. And well, this was studied by Hitchin. So for a generic point in omega 3, you can do this uniquely. There are formulas for this, omega plus, omega minus. This gives you an interesting nonlinear polarization on the space of 3 forms. So it's actually an interesting example, which was looked at by Gerasimov and Shitashvili, which was kind of a paper that inspired us. And you can calculate the effective action. So they essentially consider the classical counterpart of what we did. So if you consider the effective action in the for the abelian Chern-Simons with these polarizations, then you get a model which is essentially related to so-called Kadeira-Spencer gravity, or BCOV theory, Brzezinski-Chikoti-Oguri-Waffa theory, where the field will be again a kind of a residual field along the interval, which will now be a 1,1 form, 1,1 form on X. Well, I should just say that conceptually, the new thing here is studying nonlinear polarizations and studying effective actions with nonlinear polarizations, which brings in its own difficulty. But somehow, well, we studied that again, starting from some toy models. We understood how to do this example. But I'm wildly out of time. I apologize for that. Let me stop. Thank you.
Thank you very much. Are there any questions? Online?
Okay, maybe I ask something very
naive. So, what is the difference between so we know from like classical works that once you compute effective action for Chern-Simons, depending on boundary condition, you get one or another version of Verzumina-Witten or gauge-Verzumina-Witten or the reveal. So this seems similar, but your result, is it because your boundary conditions are different? What can you understand in your formalisms the classical story?
So, well, I didn't actually see anything quite close to the computation that we did in the literature, and I think the closest thing that I've seen was in the paper of Blau and Thompson from the early 90s. But essentially, the result there was not computed through Feynman diagrams. but it was more or less claimed from claiming that you have essentially from what we would call quantum mass equation. So from claiming the gauge invariance of the quantum answer. Here it was not claimed; it was obtained from computing Feynman diagrams.
Okay, I see. So you really claim that in your situation it's really quantum answer to all.
Yes. Yes, absolutely.
Okay. I see then. Okay, and one more question. This you showed delta operator.
Yes.
As you know that in local theory it is typically undefined as zero, but in your case, how it is defined, or
so
how do you want to regularize it? Is it non-trivial? Yeah, that's the question.
Right. So well, yes. I guess we're doing some naive regularization here. So a more proper way would be to discretize the surface sigma and to try to replace it with some cell complex or triangulation. So, well, here I guess we are just dealing with some kind of naive, most naive regularization. So, yeah, I can't say much more about it. So, of course, the computation that I was explaining here is the computation of the path integral along the interval. It should be sort of supplemented by the subsequent path integral over this group valued field, so the WZW path integral, and then sort of you would have kind of a finite dimensional space of fields remaining where you don't have any trouble understanding what is delta.
So in this case, it's rather formal.
Yes.
Well,
yeah, it is rather formal. I would say that, well, these operators, they involve some kind of integration. Well, okay, no, these are not particularly problematic. Yeah, I would say that it is somewhat formal. Yeah.
Thank you very much.